In this video, we're going to talk a bit more about max flows. So first, I want to remind you of a really important property of max flows called weak duality. This is lemma 10.1 from the book, and it says that if you have any feasible ST flow F and any ST cut ST, then the value of F is at most the capacity of ST, and that holds for any F and any ST. It doesn't matter which ones. And these two things are equal. The value of the flow equals the capacity of that cut if and only if F saturates every edge from S to T and avoids every edge from T to S. And that last part is the really critical part when we want to argue about maximum flows and minimum cuts. So these will give us a lot of useful properties to solve problems. So in particular, if we drew this out, we have, say, our cut S and T, and we have a bunch of edges crossing the cut. And so we know if F is a maximum flow and ST is a minimum cut, then each of these edges have to be completely saturated. So if these had capacities as follows, then F must be fully using them. And for any other edges that go from T back to S, we know these are completely avoided. So the flow uses 0 out of whatever was possible. So that's the image in your mind you want to keep when you're thinking about reasoning about min cuts versus max flows. Okay, so now that we have that in mind, let's try some problems. So the first problem is pretty simple, but you want to be careful about the assumptions you're making. So if I give you a directed graph G and two vertices, S and T, along with a capacity function, and then I give you this flow F, which I claim is a maximum flow, can you quickly determine whether F is a maximum flow? So can you quickly verify that F is a maximum flow? So how do we check F is a max flow? So one obvious thing we could do is just compute a max flow and check that F has value equal to the max flow. But that's not all we have to do. So first of all, if we did that, that'd be very slow. So we could just compute a max flow F star and check the value of F star equals the value of F. But if we did that, not only is it slow, but that doesn't actually prove that F is a max flow, because we have to prove it's also a feasible flow. So there's a bunch of things we really have to check. So one thing we have to check, that it's a flow. So we have to check F is a flow. So we have to check conservation. So we need the sum of all edges going into V, the flow. We need that to be equal to the sum of all edges leaving V of the flow. So that implies F is a flow because it satisfies conservation. We also need to check that F is feasible, specifically with respect to the capacity function. So this just means for every edge, we check that F of E is at least 0 and is at most the capacity of that edge. And the last thing we have to check, now that we know F is actually a feasible flow, so after all this, we know F is a feasible flow. Now we have to check that F is maximum. So now we can do the part where we just recompute a max flow, but we don't have to do that. Because remember, we can compute the residual graph. The residual and check if there exists an S to T path in this residual graph. And how do we specifically check if there's a path? Well, technically, we'd be doing a whatever for search starting at S and check if T is marked. But at this point, you don't really need to say that. We can just say check if there's an S to T path using whatever for search. So overall, the first step, that requires us to check every node and edge. So step 1, this takes O of V plus E time. Since we loop over all vertices, all ingoing and all outgoing edges. So if we're using a standard adjacency list or some kind of two-way adjacency list, we can do it quickly. Then part 2, that's even easier. That's straight up O of E. We just have to look at each edge. So again, if it's an adjacency list, we also have to touch each node, but we don't really care. And then finally, step 3, that involves creating the residual graph, which takes O of V plus E, and then doing a search in it, which also takes O of V plus E. So overall, the algorithm is O of V plus E time, which is way, way faster than O of V times E. And now overall, the algorithm is going to check condition 1, 2, and 3, and if any of them are untrue, it returns false. So overall, we return true. F is maximum. It's a max flow. We do that if and only if condition 1 is true, condition 2 is true, and condition 3 is true. And so that's the entire problem. So at first, maybe this seemed really obvious what to do, but by using a little more thought, we see that we can do faster, and there were extra conditions we really needed to check. So always be thinking about really what flows are, because they're intuitively simple, like it's water through pipes, but there is a bunch of mathematical stuff going on here. Okay, so here's another problem. So let UV be some edge in the graph. And what we want to consider is, well, what if U to V is an edge in the cut? It's an edge crossing the cut. So if U is an S and V is in T, then the edge UV is crossing this min cut. And so if that's the case, we want to prove there is no other min cut where U is in the right side of the cut and V is in the left side. So when you're tackling a problem like this, you always want to start with some kind of picture to get an idea of what the problem's really asking. So here, we're assuming we have some min cut. We have a node U. It has an edge to some node V. V's in the other side of the cut. And we know U to V is one of the edges that crosses the cut. So the capacity of that edge is included in the capacity of the SD cut. So in other words, if we looked at the capacity of this cut, it's the sum of all edges, X and S, Y and T, of the capacity of X to T, or X to Y. We know this is at least the capacity of U to V, because U to V is one of those edges. So that's the situation. And now the problem's asking about, well, what if there was a different cut that had U in the right side? So what if we moved U over here and V over here? So maybe it'll look like this, where this is now, drew that a little wrong. So we have this is now S prime, and it contains V, and now the rest of it, this is T prime. So little s is over here, little t is over here, and the edge U to V is now crossing from T prime to S prime. It's no longer in the capacity of the cut. So the capacity of this cut, S prime T prime, does not include the capacity of U to V. But it would include the capacity from V to U if that exists. So if there was an edge from V to U, that would be counted in the cut. So that's kind of the situation we're considering. Can something like this be a min cut? So the problem's asking you to show it's impossible. So really you want to show that the capacity of S to T is strictly less than the capacity of S prime T prime. So the simple mathematical approach might be, okay, somehow prove that ST is smaller than S prime T prime. And you could do that maybe with some kind of exchange argument where you slowly swap edges and eventually you get to U to V and try to argue that it was somehow a smaller edge. But the mathematical approach is going to be very complicated, so let's not argue about cuts specifically. So the key thing here is, even though the problem's about cuts, weak duality is going to be critical. Think about flows instead. That's how most of these problems end up going, because that's the key power we have is the max flow min cut theorem. We know the flows and cuts are related, so if the problem's too hard when we just consider one of them, well, then we can convert it to the other version and see if that helps make it easier. So how can we use that theorem? Well, specifically, we're going to use lemma 10.1 again. So what does it say? Well, let's just consider any max flow. So just pick a max flow, F. So by the lemma, we know for any min cut, and I'll call this xy, F must saturate, in other words, fully utilize the entire capacity, any edge x to y crossing the cut, and must avoid edges y to x crossing in the reverse direction. So that's what we know by lemma 10.1. So in particular, we know that F must be saturating every edge from S to T. So all of these edges are saturated, including U to V. So in particular, since by assumption ST is a min cut and F is a max flow, well, we know they're equal. The capacity of ST equals the value of F since it's a max flow. And so that lemma implies that F saturates U to V. So in other words, the flow from U to V is at its highest it could be. It's at its capacity. On the other hand, since S prime T prime is a min cut, it must be the case that F avoids U to V. So F of U to V equals 0. Why? Because in this picture, the edge U to V crosses the cut in the opposite direction. So over here, U goes from T prime to S prime. So by that lemma, it would have to avoid it completely, so it'd be 0. And clearly, this is a contradiction if u to v is an edge. So unless the capacity of u to v is 0, in which case it wouldn't even count as an edge in the min cut, then we have a contradiction. So this is a contradiction that u to v is in the min cut. And so S prime T prime cannot exist. Or in particular, it cannot be a min cut. So that's the entire proof. So if the edge is included in a min cut, then we could never have the nodes reversed. There's a clear structure between these two nodes that has to be maintained. This one has to be in S, and this one has to be in T. Because otherwise, it would have to be both saturated and avoided at the same time, which can't happen. So that completes the proof of this claim. And the key idea here, again, is if we just try to reason about cuts and do some kind of weird exchange argument or other thing, it gets very complicated. But if we just think about flows, it was super easy. By picking any max flow, we can reason about the value of the flow in the cut by using weak duality, and then we know information about whether the edge was saturated or not, and that gives us our contradiction. Okay, so now that we have these basic ideas in mind, we can move on to a more complicated example. So this problem concerns unique max flows and min cuts. So in general, we're cool with computing any maximum flow, but this problem asks, is it true that there's a unique one? So there's a unique flow with maximum value. And similarly, is there a unique cut with minimum value? So to start off again, we want to draw a picture and get an idea of what these things look like. So let's start with C and D, where we want to come up with examples to give us an understanding of the structure of this problem. So for the first one, we want to find a flow network that contains a unique maximum flow, but many different minimum cuts. So this one's pretty easy. Consider the following flow network. So let's say the capacities are 10. So clearly the max flow in this graph is going to fully saturate both edges. So the max flow value is 10. And there's obviously only one function that does that. If we decreased or changed the flow on any edge, then it's no longer a max flow or it's not feasible. So there's only one max flow, which is in green, just fully saturate both edges. But there's, two min cuts. So the set of S and then the set of VT, that's one min cut, and the set of SV, set of T, these are both min cuts. So why? Well, if we draw the picture, that's one of the cuts, and this is the other cut. Clearly, both of them have capacity 10 because there's only one edge crossing the cut in both cases. And their capacities are 10. So okay, we have an idea of what it looks like when there's a unique max flow, but many min cuts. So now let's do D. Now in D, we want to find a flow network that has many, or a single min cut, but many max flows. So what would that look like? Well, you could think of something similar. We have S, it goes up to a node U, goes down to a node V. So here we're going to give the flow multiple ways it could go, but a single bottleneck value. So this is going to be our main bottleneck value there, but we'll make these larger. So we'll allow these to all be 15, but obviously at the end, the bottleneck is 10. We can't do any better than that. So here, the max flow again is, one option would be this. Another option, which is equivalent, would be this. And then these would have to be zeros, these would have to be zeros. So there's two primary max flows, and you can also take a combination. So you could have 5 going up the up path and 5 going down the down path. Either way, there's a bunch of max flows, and they all have value 10. But there's only one min cut, because there's only one critical bottleneck. So the only bottleneck here is right here. So only min cut technically, to make this work, we're going to add one more edge right here. Let's say with capacity 1, because otherwise this example wouldn't work, because you could have done something like actually it would have worked anyway. Yeah, that's still fine. I was just thinking how, well, maybe if you took just the bottom part, then it's still fine, but you still have that 15 popping out. So you want to think carefully about these counterexamples. So the only min cut is the one where we have S, U, V, W. So basically everything is loaded into the left side and only T is on the right side. And clearly its cut value is 10. Its capacity is 10. So here we have a bunch of max flows, but only a single min cut. So there's examples of networks with both cases. So now that we have the idea of what we're being asked, let's try to come up with some algorithms for them. So the first thing we want to do is determine whether a given flow network contains a unique maximum flow. And generally, we're going to assume we're given a flow, a max flow, F star. So the reason we do that is because generally we want it to be faster than recomputing a max flow from scratch. So even if we're not given the max flow in advance, we can compute it, but we want the other steps in the computation to be pretty fast relative to the initial step. So we want the first step, compute a max flow, to be the hardest step in the algorithm. The rest of it should be pretty simple. Because ideally, computing an entire max flow should be harder than just checking whether one is unique. There seems to be a difference in difficulty there. So let's solve this. So first thing we're going to do is we have our max flow F star, which we either compute or we can assume is given to us. And now we want to think, does there exist a F prime that's a max flow, but different from F star, which is the one we're given. So what does it mean for two flows to be different? Well, that just means there exists at least one edge for which F prime of E is different from F star of E. So there has to be at least one edge where they send different amounts of flow down that edge. Okay? So there's going to be a key characterization that's going to help us. So we'll have a lemma. So the idea here is the residual graph, GF star, has a positive capacity directed cycle. So we can find a directed cycle in GF star of positive capacity which if we remove everything with zero capacity anyway, this just means any directed cycle have capacity greater than zero. So the residual graph has a positive capacity directed cycle if and only if F star is not unique. So why is this? So I think the first part's pretty clear. So if there was a cycle, then we can easily create a new max flow. So if there is a positive directed cycle in the residual graph, then we can just take F star and then push flow around the cycle to get a new flow. And now clearly the new flow is a flow, it's a feasible flow, because as we argued in the proof of Ford-Fulkerson, that whenever you find an augmenting path, or whenever you find any kind of cycle as well in the residual, it corresponds to a flow in the original graph, because conservation will hold, and it'll be feasible. We'll never push flow down below zero or push flow up beyond the capacities. So this part's true just because the proof of Ford-Fulkerson but to get a little reminder, the idea is if you push flow down a cycle, just say some unit then conservation holds because if you have some cycle, you put x on each edge, then the inflow in any node, say v, is inflow x and outflow x. So whatever it was before, so before the conservation, so this is like f star plus x, or f star minus x. Since f star was feasible, the total conservation at v was 0. And so when we add x to both edges, we've added a net increase of x, or we've added an increase of x and a decrease of x, so we get a net difference of x minus x, which is 0. So overall, we can push flow down a single cycle, and it'll still be a flow. Conservation still holds. That's the idea, but you can get more details in the proof of Ford-Fulkerson. So the other thing to notice is the value of f is equal to the value of f star, because remember, the value just has to do with the net flow leaving S. And since a cycle won't affect the net flow leaving S, because we are adding the same amount we removed to every node, this will have the same value. Okay, so this is especially clear if the cycle doesn't touch S. So if the cycle doesn't touch S, then it's obvious. But if the cycle does touch S, it still holds, because again, if this was, say, S, the amount we've changed the net flow leaving S by is nothing. The amount that we added to S is the same amount that we've removed from S, because the ingoing edge is going to remove flow from S, or from the value. Okay, so that's a flow. In particular, it's not critical to the problem, but remember that when we push flow down a path or a cycle in the residual graph, it's not necessarily a path or a cycle in the original graph, because sometimes an edge from a node could mean reduce the amount of flow. So in general, for a closed walk, it might not literally be a cycle, like we're not actually pushing x through everything. We might be subtracting x on some, but adding x on others. But if it's specifically a cycle, then it is true that we're actually adding x or subtracting x from every single edge in that cycle. So just to keep in mind that the residual, things in the residual aren't exactly the same as things in the original graph, but for this specific case, the cycle in the original graph corresponds to a cycle in the residual, or reversed. So it might also be reversed, but either way, it's still a cycle. So this part's easy. We just take the original flow f star, we just push flow down some cycle, and we get a different flow. That's also maximal. So now the hard part is, if there's no unique flow, can we construct or find a cycle? So let's suppose there exists f prime, a different max flow, so if such an f prime exists, let's consider the difference function, which is going to be f prime at E minus f star of E. So for each edge, this quantifies how different the flows are on that edge of f prime versus f star. So the first thing to notice, delta is called a pseudoflow. So what this means is it satisfies conservation, but it could be negative or it could be larger than the capacity. So this thing could be negative, but it'll still satisfy conservation. So why does it satisfy conservation? Well, this is just because of the fact that both its constituent parts do. So if we took delta of V, if we looked at the net flow or net pseudo-flow leaving V, this is the sum of all U to V of delta U to V minus the sum of all V to W of delta V to W. Now this, by just applying the definition, is f prime of U to V minus f star of U to V, and then minus all of these edges leaving V of f prime V to W and f star V to W. Now we can just rearrange the terms. So if we just look at f prime U to V minus f prime V to W and f star U to V, f star V to W, then we know those will be 0. So the yellow parts, these sum to 0, and the orange parts also sum to 0. And this is because both f prime and f star satisfy conservation. And what's written above is just the conservation formula for both flows, just subtracted. So either way, it'll just be 0 minus 0, which equals 0. So that's why it satisfies conservation. So let's make another page. So we know it satisfies conservation. Does that really help us? Well, because f prime and f star are different, we know there exists some E with f prime of E not equal to f star of E, and that implies delta of E is not 0. The only way for delta of E to be 0 would be if the flows of both are matching on edge E. So we have there's some edge E with non-zero pseudoflow. So let's consider it. So let's say it's U to V, and this has some delta that's not 0. So in particular, let's first assume it's greater than 0 to illustrate the idea. Now, since delta is a pseudoflow and so has conservation, what do we know about the flow leaving V? Well, we know the net flow leaving V is 0. So either the edge leaving V also has delta greater than 0, so that the difference at V equals 0. Or, if that doesn't happen, it must be the case that there is an edge going into V from some other node X that has delta negative. Either way, at V, the total will be 0. So either we can have incoming pseudoflow being positive and negative, and so it cancels the 0, or we have incoming flow positive, but outgoing flow also positive. In either case, there exists another edge, E prime, with delta of E prime not equal to 0. In particular, let's rename these. So let's say it's E1, and let's call this E2. So either way, we have some E1, and we have some edge that connects to, that's touching the endpoint of E1, i.e. some edge touches the endpoint of E1, which is V, with non-zero delta value. So we know that has to be true because of conservation. So it's one of these cases. And so we can keep doing this because this argument repeats. So it's also true if you had, say, U to V was delta less than 0, it's the same thing. The only difference is now this one's going to be delta greater than 0, and this one will be delta less than 0. And you can also do the same thing with the incoming edges too. Either way, we can do this. So what will this be? Well, we can keep, so inductively, we can keep following or finding edges EI that touch the endpoint of edge EI minus 1. Why? And that's because of conservation. If we ever arrive at some node by some non-zero pseudoflow, then we have to be able to leave that node by some other non-zero pseudoflow. Otherwise, the total net change at V would not be 0. So just like in Eulerian circuits, every time you enter a node, because it has degree even, there must exist a way to leave it. So it's the even degree idea from Eulerian circuits. So we enter, and then we can leave. Okay, so all of this is happening in the original graph. Note that we're finding edges that touch the endpoint, but these aren't necessarily cycles, right? So here, we can't literally go backwards. This edge is going towards V. Now the key thing is this is the original graph. So what we're going to argue is that in the residual graph, this will actually go in the direction we want it to. So what this does is it finds an undirected cycle, i.e. it's a cycle if we ignore the directions, and we'll show it's directed in the residual graph. So that's the next step. So there's two cases. So let's say delta of E, some E on our path. So I guess one other thing to mention is the reason it's a cycle is because eventually we repeat a node because it's finite. This is something we've argued many times before. So overall, it'll have a repeat, and so we found a cycle. So now if we look at our cycle, which is some subset of the E's, so let's say EJ through EK is a cycle of that form. And let's say E is some node on that cycle. So the first case is when delta of E is greater than 0. That, by definition, means that f prime of the edge E minus f star of E was greater than 0. So what does that mean? Well, that means f prime is the larger one. And so we know f star is not saturated. Specifically on edge E. Why? Well, because f prime is feasible, we know f prime of E is at most the capacity of E. And because f star is strictly smaller, there's still some flow we could send down f star to make it larger for this specific edge. So if f star is not saturated, then we know we can increase it. And so in the residual graph of f star, its capacity will be that difference. It's the capacity of E minus f star of E, which is positive. So whenever delta of E is positive, we have this next edge on the cycle will be positive, capacity. And that also means it's going in the right direction. So now the other case is when delta of E is negative. Well, this is the opposite case. So here we have it's a less than. So f star is the larger one. Well, remember, when that's the case, we can decrease the flow on f star. So here this is feasible, so it's at least 0. So now we know that the residual capacity, so let me draw it in green again. So f star of E not avoided. So in the residual, we have C of f star of E, specifically the opposite of E. This is going to be, so let me emphasize it's the reverse, E reverse. So if you went the opposite way, this will be equal to f star of E. Because remember, f star of E is the amount we can remove from that edge and still be feasible. So if you remember, in the residual, for any u to v, we always have this edge u to v and v to u, where this is how much we can increase u to v by this amount. And the reverse edge is how much we can remove. from U to V. And so that's where these ideas are coming from. So in either case, what have we found? Well, we found we have an edge of the right direction, and that's positive in both cases. So remember, in the case above, if we're going forward, that means delta is greater than 0. We need the next edge to be delta greater than 0. And in the residual, this will have delta greater than 0. Or it'll have residual capacity greater than 0. That's the forward case. But when delta is less than 0, it's backwards. But the key is in the residual graph, we know this has positive flow value, and so it'll have a reverse edge in the residual that has positive flow or positive capacity, representing how much we could have removed from that edge in the original. So in either case, we get, so each edge, EI, is in the right direction to make it a cycle and has positive capacity in the residual, and so EJ through EK is a positive directed cycle in GF star. So it was a lot of work, and it basically forced us to create an algorithm to find the cycle, but now we have proved this lemma here. So if GF star has a positive capacity directed cycle, that can happen if and only if F star is not a unique max flow. So at the end, what's our algorithm? Well, if we're given F star, we just compute G of F star and run DFS with cycle detection, or whatever for search with cycle detection. And output true, it's unique. Exactly when or only when. So we output true if no cycles found. Otherwise false. And so because we're just doing a DFS with cycle detection and computing the residual graph, it's going to be O of V plus E. So it's actually linear time to check, given the max flow, if it's unique. Or if we had to start without a max flow, well, we can just do an additional O of V times E to compute the F star and then do the remaining steps. So either way, it's not going to be harder than finding a max flow. And that's the key ideas. Cool. So that was a lot of work just to figure out if a flow is unique. But finding if cuts are unique is actually going to be easier. So we've now completed this part. So this part's going to be a bit easier now. So how can we figure out if a cut is unique? We're going to use a similar idea. It'll be a little easier. So what are we going to do? So again, let's think about lemma 10.1. So if we have some flow in the residual graph, so let me phrase it like this. Because all the edges of a cut, specifically a min cut, are saturated by any max flow F star, we know in the original or in the residual the edges of the cut don't exist. So let me call the min cut ST, for example. And this is because they'll have zero residual capacity. And we can essentially remove those from the graph. So in terms of a picture, if we have that, let's make this our residual graph. We have S, we have T, and maybe this is one of the ST cuts. We know all of these edges don't exist in the graph. And so it basically splits the graph GF star into components. So this splits GF star into separate components. They're not literally different components because there could be edges going backwards, but they're essentially different components. Now the key thing here is, remember, not only are things saturated, but things are avoided. So any edge that goes from T the other way is avoided, and so it has absolutely no amount of value there. And so it will have, because it's avoided, it won't show up as this edge, right? Because that's how much we could have sent the other way. So either way, there are no edges from S to T in GFS star, which is why for Ford-Fulkerson, we computed the reachability set of S. But this doesn't just apply to the first reachability set. So this gives us one min cut, but there's actually more. So here, this is like a new component, and maybe there's another set of edges that don't exist. And maybe there's even another one. So there could actually be several of these components. So I'll just call them C1, C2, and each of these correspond to the S in some min cut. So it's not important that you pick the first S, the one closest to little s. As long as you have any of these components, these correspond to min cuts. And that's just because the flow is completely saturating all of these edges and completely avoiding the others, and that's why you can't reach between these components. So any pair of components, or any blue line basically, each blue line corresponds to a min cut by the lemma. In particular, in the original Ford-Fulkerson, we focused on the reachability set of S, which is essentially the min cut closest to S. On the other hand, this will make T very large. But we can do the opposite. We can consider everything that can reach T. So everything in this side, and then if we make that T and we make the big part S, that's another min cut. So because of this whole idea, this implies if we take T to be everything that can reach T, little t, and S is V minus T, it's everything else, then this ST, let me actually call it ST, S prime T prime, because I'm assuming we have a different ST, which is from Ford-Fulkerson, then this one is also a min cut. And And why is this? Well, because the argument from before is if you can reach T, that means you found a path of non-saturated edges. If everything crossing a cut is saturated, then it's a min cut. So if there's still some that are saturated but not all, it can eventually reach T, and so it wouldn't be a min cut. So in particular, the first blue line, where we can no longer cross over to T, that will become the first min cut that's closer to little t. And how do we actually compute this? Well, this is called the reach inverse of T. So this is something we talked about when we discussed strongly connected components, because it's very similar here, right? Each of these components is similar to a strongly connected component, but it's not exactly the same. And this is the set of things that can reach T. So how do you compute that? Well, remember, we can just do reach of T in the reverse graph. Okay, so we know this is another valid cut. So if this is a different cut from ST, well, then clearly they're not unique. So if S prime is different from S, then found another min cut, so not unique. But if S prime equals S, then it's the unique min cut. So why is that part? Well, it's based on this idea. So every single min cut causes a new blue line to be made, representing all the edges that are fully saturated and so don't appear in G of F star. So if there are no other blue lines, there are no other min cuts. So if the only blue line is exactly the same line as the one generated by Ford-Fulkerson, that means there's no other min cuts. So another way to think about this is the Ford-Fulkerson min cut is the one closest to S. And so if we try to generate other min cuts farther from S and fail, then that must be the only one. In particular, the most extreme one would be the one closest to T. So if the most extreme min cut, different from ours, is the closest to T, and that blue line ends up being the same as the one closest to the original, then obviously that's the only min cut. So that's the idea. So what's the algorithm? Well, assuming we're given F star, all we have to do is do reachability i.e. whatever for search of T in the reverse graph, the reverse residual graph. We also have to compute the reverse residual graph, but that's not going to be too hard. So after building it, then what we do is we define S prime T prime based off of that with the formula above. So T prime's that reachability set and S prime's everything else. So T prime is the reach of G reverse F star of T. And then just check that T prime equals T. Where T, this T is defined as the reachability set of S in GF star without everything else. So it's V minus that. So essentially this is the T from Ford-Fulkerson. That's what this T is. So how do we check they're equal? Well, we just loop through every node and check if the node in T prime is present in the node of T. But you can also do it in more efficient ways. So I'm just going to assume it's constant time to do a check for each individual node. So if they're equal, we're done. But really, we just need to check, is the intersection different? That's really what we want to compute, because that's even faster to do. And if so, we output false, else it's true. So if we can't find any node that's different between them, then we know the min cut is unique and we say true. So overall, the runtime again is going to be O of E plus E. But if we need to compute F star, then it's also an extra VE to get F star. And that is the full algorithm. So this one, the algorithm's kind of weird, right? It's kind of wacky. We're doing this reverse search and a forward search, and then doing a comparison, but the proof is a little easier, right? It's a bit clearer what's going on here. Whereas for the first algorithm, the algorithm's pretty simple. We just find a cycle, but it's very complicated to figure out this characterization. So here's just another example of where there's a trade-off between the complexity in the algorithm and the complexity in the proof. Okay, so now that we have the ability to check for minimum cuts, unique minimum cuts, we can talk about the best minimum cut. So the best minimum cut is a pretty simple idea. It's just saying if you have multiple minimum cuts, can you just pick the one that has the fewest number of edges? So for example, if you had some ST cut and it had maybe 4 edges, and there was a different S prime T prime cut and it had 3 edges, you want to prefer the one with fewer edges. But they're both min cuts, so both have same capacity. Obviously, if there was a cut with only 1 edge, but it had a huge capacity, we still wouldn't want to pick that one. It's just when we have multiple choices of a min cut, we tie break between them based on the number of edges. That's the idea behind a best min cut. So how could we do this? Well, your first instinct might be just modify Ford-Fulkerson to prefer fewer edges. Just like maybe for Dijkstra, you could do the same thing. You can just take Ford-Fulkerson whenever it's doing short augmenting paths, make sure it uses very few edges when you look at the final cuts somehow, and you could probably figure out some way to do that. But generally trying to do this gets really hard because you need to make sure you're not breaking Ford-Fulkerson or some other algorithm. You want to make sure what you're doing is exactly correct, and it just gets really difficult to figure that out. So instead of doing that, what we're really going to do is a graph reduction. So let's just define a new capacity function. So this is going to be the original capacity times some number, and then plus the number of edges from that cross the cut. So I'm defining this to be the number of edges crossing the cut. So in this example here, that n variable will be 3, whereas here the n variable would be 4. And so the idea behind this is if m is large, then the priority is making the capacity small. So if you want to minimize this new capacity function, then you can do that by minimizing the capacity of the cut that has the largest impact, since the large scalar makes a large impact on the size of capacity of ST. Whereas if you just change the n variable, it's not going to have as much of an impact if this capital M is huge. So the idea here is we're prioritizing making the capacity small, but if you had a bunch of cuts with small capacity, then you're going to tie break by making the n small. So functions as a tiebreaker. So that's the idea. And now what we could do is some kind of greedy thing where we prefer small capacities in Ford-Fulkerson, but we could actually just make a new graph. So instead, we're going to create a new graph, just like usual with graph reductions. But really, we're just creating a new capacity function. Not on the sets, but on each edge. So what's the new capacity function? Well, for any edge, the capacity of the edge is going to be its original capacity times m plus 1. And so if we do that, then when we consider the capacity of a cut in this new graph, so the capacity of any ST is now going to be the sum of all edges in that cross cut of C prime of E, and this is going to just give us the sum of all E crossing of the original times M plus the sum of all E crossing. And so this part is just going to be the original. So we get MST, where this one is in with respect to the new capacity. So let me say with respect to C prime, this one's with respect to C. And that other sum, this is just 1 for each edge crossing, and so it's just the number of edges crossing. So this is going to be N of S V minus S. So any capacity of a cut in this new graph is equivalent to the formula in the old graph. So this is giving us exactly what we wanted. So now all we have to do is compute a min cut in G prime, but remember it's just C prime instead of C. We're not changing any of the nodes or anything. And this will be a best min cut. Okay. So we've reduced it to just solving the original min cut problem in a slightly different graph. So now there's a few key questions like what should capital M be? Well, for us to prefer capacities over the numbers, we need capital M to be greater than, always greater than the n function. So what's the most number of edges that can cross a cut? Well, it's going to be something like n squared. Specifically, it's like n squared over 2, but just to be safe, we'll do n squared. So the details, we will make m equal to n squared. That's also called v squared. I'm just using n here to be the number of nodes. And then overall, it'll just be O of v times e time, because we're just computing a min cut. Now, it's critical here that we're using, say, Orland's algorithm, not Ford-Fulkerson. If we used Ford-Fulkerson, remember, it depends on the size of the max flow. And what we've just done here is we took a capacity which already could be big, and we blew it up. We made it huge. So the max flow value in this graph could be really big. So if we didn't use Orland's and we used Ford-Fulkerson instead, we'd get something very slow. Even if the original ones had unit capacity, because now we have this capital M there. So just wanted to point that out. We've been using Orland's throughout all of these so far. I don't believe any of these you could have used Ford-Fulkerson for if you computed F star from scratch. So keep that in mind. But now we need to prove this is true. So lemma, if ST is a min cut in G prime, then, well, we really want this to be an if and only if. So that's a min cut in G prime if and only if the same cut is a best min cut in G. But we'll just prove one direction of it because that's the most important one. So let's suppose we have a min cut in G prime. Then what can we say? Well, let's suppose for contradiction, there was a smaller cut in G prime, or a smaller cut in G. So let's first just show it is a min cut. So we want any min cut in G prime to be a min cut in G, and then we can worry about whether it's best or not. So let's say it was a min cut in G prime. So it minimized the function. And now let's say for a contradiction, there was something smaller. So let's say in G, there was some S prime, T prime of smaller capacity with respect to the original capacity function. So what does this mean? Well, that means the cap function, or if we consider just capacity with respect to C prime, so we have S prime, T prime. With respect to C prime, this is going to be the capacity of S prime, T prime with respect to C plus some number of edges, S prime, T prime. Now, what do we know about this? Well, it's also times M. Now, by assumption, M is bigger than N, so this is at most the size of S prime T prime with respect to C times M plus in M. It's actually strictly less than. Okay, so then this is equal to 1 plus M, the capacity of S prime T prime with respect to C. And then by definition, by our assumption, that's less than 1 plus M S T with respect to C. But now what is this? Well, this is going to be, at most, the capacity of ST in C prime. So if this was true, notice that in our new graph G prime, this cut was a smaller cut. And so we have a contradiction because we're assuming in the graph G prime, this was a min cut. So this contradicts that ST was a min, well, let me just say it like this. ST was a min cut in G prime. Okay. So we know it must be a min cut in G as well. So if we do this process, we do get a valid min cut in G. But now the question is it truly a best min cut? Now we're going to do the same thing again, but now look at N instead of looking at the first part. So to show it's a best min cut, well, if we compared it to any other min cut, we get the same issue. So now we have, let me make one more page. So now we have S prime, T prime, and C prime. Well, this is equal to S prime, T prime, and C times M plus some N. And now we're assuming that we already proved that this is actually a min cut in G. And so, well, this is the same as ST, C times M. Now, by assumption, we're assuming it's a best min cut, so this has to be smaller. So this is smaller than the number of edges between S and T, because by our assumption, we're assuming S prime T prime has fewer edges than S and T. But again, this is exactly equal to ST and C prime. So again, if this was true, and specifically I'm making this a less than, not a less than or equal, if this were true, that contradicts that ST was a min cut in G prime. And so in either case, we know that ST is a min cut in G by the first thing we proved, and by the second claim, it has the fewest edges. So is a best min cut. So this statement probably was kind of obvious that we should do this, but as you can see, the formal proof does require some key algebra that we have to work through. And that's the full proof. So overall, what's our algorithm? Again, in O of V times E time, we can just basically modify the original min cut algorithm implicitly by using a different graph as input. So overall, we compute a min cut in this slightly different graph, and then the output solution will be the same. And that's all.